Okay. Hello everyone, my name is Mladen and thanks for coming back from the beach to listen to this talk. So I'm going to talk about my joint work with Han Liu, and this is work on marginal regression applied to marginal regression problems. Just a second. So in this problem, we are going to consider a particular multitask regression problem. So we have n sample points coming from these t regression problems. And so we have xi being a vector of predictors, which is a random vector drawn from normal 0 sigma. This is a p-dimensional vector, and epsilon ti is an unobserved noise, and yi's are dependent variables arising from this model. These are observed, and so based on xi and yi, we would like to infer something about unknown regression coefficients. And in this multitask regression problem, we're going to assume that the regression coefficients are somehow related between different tasks. The noise is going to be independent from the predictor vector. Okay. So onto this multitask regression problem, we are going to study it in particular high dimensional setting when the number of variables is much larger than the sample size. And we are going to assume something about the sparsity of regression coefficients. In particular, let us denote ST a set that indexes non-zero components of regression coefficient beta t. And then S is going to be a union of these sets. And so under the assumption that the set S is small, comparable to the sample size n, we'd like to make an estimator S hat based on the data that correctly recovers the true unknown support set S, or we'd like to say something about at least the estimator that contains all the relevant variables and some additional random variables. Okay, but in this particular talk, I'm going to focus on exact recovery of relevant variables in this multitask linear regression model. Okay? And so what are we doing pictorially? We have a matrix of regression predictors. And so this is a n by p matrix. It's wide because we have many more predictors than the sample size. Then we have a matrix beta of unknown regression coefficients. It is assumed that only few rows of that is non-zero. These are these. And so we would like to estimate S from observed Y and X. Okay? And so you may wonder, why is this a useful model? And I'm going to present you two applications where this model has been successfully applied to. First application comes from computational biology, and the problem is called gene association mapping. In this particular problem, X is observed gene sequence, and Y are some phenotypes. For example, phenotypes could be concentration of genes in a particular cell. And then the question of interest is, how can we identify positions in this sequence that are somehow related to phenotypes? And this is a high dimensional problem because currently we're getting something like 500,000 of these predictors, and the number of tasks that we deal can be in thousands. Okay? And so instead of looking at only one phenotype at a time, we would like to jointly look at locations that jointly affect a number of these tasks in order to boost the signal-to-noise ratio. The second task comes from cognitive neuroscience, and here we have the following experiment that we present a person, a word, and we measure fMRI activation levels. And then we would like to learn semantic basis. That is, for each word, we encode semantic meaning of that word by measuring what is the co-occurrence of this word with a large corpora, with each word in a large corpora. And then we would like to select these semantic bases so that when a new word appears, we can represent it in these basis elements and potentially be able to predict the outcome of an fMRI scan without actually performing one. And so Han Liu won a Best ICML paper a few years ago on an application of this. And so currently what researchers do in this problem is they solve a convex optimization problem like this. They minimize squared loss subject and plus some penalty. And this penalty encourages sparsity. So this penalty guides the estimator, or biases the estimator toward solution that have only few non-zero rows. And so in particular, 3 penalties are popular. First one is a Lasso penalty. And this corresponds to performing penalized regression on each task individually, where the last 2 ones perform penalized estimation jointly over all tasks. And so once a researcher fits this objective, the support that is recovered can be obtained by looking at which rows of the regression coefficients are non-zero, and they claim this is a set of relevant variables, and maybe they want to perform some further validation in the field of interest, but that is what is done. Now, what the problem, or one problem of this approach is that when we have 500,000 predictors, it might be expensive to solve this particular convex optimization problem. So researchers have come up with a lot of efficient algorithms for solving the multitask linear regression problems with various penalties. However, still, it's a challenging problem to solve regression problem when the number of predictors is in 500,000, say. Even rules that kind of like can discard certain features before the optimization problem is solved are not always useful or do not reduce the dimensionality to something feasible. And so in this talk, I'm going to discuss a marginal regression, which is quite old procedure, as a tool for quickly selecting the set of relevant variables. And in the first half of first part of the talk now, I'm going to talk about marginal regression and how it's related to single task learning, and then we'll see how those results can be extended to multitask learning problems. Okay? So marginal regression, I think of it as an efficient alternative to Lasso for variable selection. So I'm not saying anything about prediction or consistent recovery of the regression coefficients, just variable selection. So what we do in marginal regression, we compute marginal regression coefficient between each covariate j, each feature j, and the output y. And let's call this mu hat j. Then we sort absolute values of these marginal regression coefficients in descending order and denote r hat j the ranks of these coefficients. And then we simply estimate the support set, or the set of relevant variables, to be the k largest coefficients. So I'm going to tell you later how to pick this k, but we can pick any k from 1 to p and call this the set of relevant variables. Now what I would like to maybe discuss later is under what conditions can this set actually recover the true set of relevant variables. So furthermore, like marginal regression has been analyzed recently, or it has been revived. Even though it's a quite old procedure, it has received certain interest in the past few years. It has appeared in Fan and Wolf paper. Wasserman and Reuter from CMU had a paper on it, and also Genovese et al. Had a paper on analyzing marginal regression for single task learning. So in our paper, we perform a sharper analysis and extend marginal regression to multitask learning. So why do we care about marginal regression? Let's reiterate that once again. So it's computationally efficient. It can often be used as a two-step tool where in the first step dimensionality is reduced, and then in the second step we perform further cleaning, and I'm going to discuss that towards the end of the talk. And then second thing is that, for example, lasso requires that variables are not highly correlated in order to be able to pick the true set. And if we reduce variables and then fit lasso on the second split of the data, the variables that are remaining are going to be much less correlated than on the full data set. And finally, one benefit of marginal regression is that the number of variables can be selected in a data-dependent way that I'm going to discuss later, in a very simple data-dependent way. Okay? And so let us just recall what are the properties of marginal regression. And so if there is no noise, then this coefficient gamma n would be 0. And what we need for successful recovery of true regression coefficients is that the marginal coefficients for the set of irrelevant variables, the maximum guy of those, is smaller than the minimal marginal regression coefficient for the set of relevant variables. And there needs to be a gap between these two when we have noise. And this gap is of this order. Okay? And if this is satisfied, and we know the support set, the size of the relevant set, then this statement holds with very high probability. Now the question is, I'm going to tell you later, how do we actually pick this S in a data-dependent way? But under some strict conditions, and I'm going to discuss these conditions, these are sort of necessary and sufficient conditions for marginal regression to successfully recover the support set. Okay? And the proof is very simple. We need to show that the maximal empirical marginal regression coefficient for the set of irrelevant variables is smaller than the minimum marginal regression coefficient for the set of relevant variables. And we write out what this coefficient is. We can sort of bound this term by substituting the empirical covariance matrix with the true covariance matrix, and then apply union bound to obtain something of this order. And similarly, we can lower bound the term on the right-hand side, which combining gives us the bound on the previous slide. Okay? And so the proof idea for this part also carries to multitask regression problems. Essentially, the mu hat j in the multitask regression setting is going to be substituted by something else, but the structure of the proof is going to be the same. And so I previously told you we can easily select the number of relevant variables, and so here it's how. Recall that rj denotes the rank of a variable j, and so let's index jk, the variable whose rank is rk, whose rank is k. Hat vnk is a span of columns of the variables that are selected, first k variables that are selected. Then hk denotes the projection matrix with Rn. And then we form certain statistics psi n k, which is of this form. It essentially tells us how much signal is there in y when we use one more feature to predict y. So essentially, if this quantity is going to be high as long as we are adding relevant variables into our support, and once this quantity falls below a certain threshold, we need to stop. Okay? And so here it is. If I look at the maximum k such that this quantity, this statistics, is smaller than some threshold. So this is the last time that this quantity falls below certain threshold, then we need to stop adding elements into our support set. And under certain assumptions, this quantity gives us actually the correct estimate of the size of the number of relevant variables. Okay, and so these assumptions are the same as the assumptions of theorem 1, plus some assumption on the minimum size of the regression coefficient beta j. And so these are sort of standard assumptions in the lasso literature as well. Okay, so this is great. We can now move on towards multitask learning, how marginal regression can be applied in that setting as well. Okay, and so as before, we compute marginal regression for each feature and each task. Then we have a function psi, which is a scoring function, takes as an input a vector mu hat tj, index for all tasks, and we are going to rank our features based on this scoring function. And again, this set of the support that is recovered can be taken just to, we take the largest, the features, the k features with the largest score. Okay, and so the assumptions are sort of complicated, so I'm going to present you only a simplified version of our results. For other results, please refer to the paper. And so here I'm showing you only if the true covariance matrix is identity, and the scoring function is the L2 norm of the marginal regression coefficients. Then we have the L2 norm of these regression coefficients, the true regression coefficients for irrelevant variables, plus this needs to be smaller than the minimum here. Okay, and so essentially this quantity is equal to 0 in for j in S complement. So we require we have some lower bound assumption on the set of relevant regression coefficients. Okay. Okay, and just to compare with the set, what would we require for the single task regression if it was independently applied to each task separately? We observe that this quantity here is much larger than quantity in here. So there's a clear benefit of using the learning from the tasks jointly. Okay, and so as before, we can select the number of relevant variables in a data-dependent way. We modify the statistic and we modify the threshold, but sort of the idea is the same. At some point, adding more variables does not help much in predicting y. Okay, and we can consistently recover the set of relevant variables. Okay, and so what I've talked about is what are the conditions under which marginal regression can recover exactly the relevant support or the relevant variables. And so the conditions that are required are very strict, very strong. And so maybe a more feasible goal that we can hope for is, can we hope for some partial recovery? Can we have maybe loss in terms of Hamming distance or false discovery rate? So that's something that is of interest later on. And so in this paper, we also show what is the lower bound on Hamming distance. So essentially, although we consider only the conditions when the support recovery can be exactly recovered, we also consider lower bounds on estimation procedures that return a support set that has low Hamming distance between the true set and the estimated set. And so we have only partial results towards that. So screening by marginal regression sort of achieves this same Hamming distances as the lower bound suggests. But then at this time, we don't know exactly what should be a second step in which we would clean irrelevant variables that are left in the model once we have performed marginal regression. And so it is, even in the single task setting, if a cleaning is done using a lasso, that is a suboptimal procedure. So even one way we can think of, like, once we reduce the dimensionality to something much smaller, we can apply maybe a convex procedure like L1, L2 penalization for the regression problem. But that doesn't seem to work. So something more sophisticated should be used to further remove the variables once we have performed screening using marginal regression. Okay, and with that, I'm done.
I have a general question. Another way of dealing with this kind of problems will be to impose a low rank restriction on your matrix, the coefficient matrix, as for example done in reduced rank regression, rather than using sparsity. Can you comment on that type of method?
Right, so when we're doing low rank recovery, what we're doing, we are essentially rotating our original feature space so that in the rotated space we can select few features. So in some sense we are learning new features, whereas here we are staying in the original space and doing feature selection on the original space. This has benefits when domain scientists want to interpret results. Sometimes when you use these factor models where we learn factors and then represent our data in terms of factors, the factors correspond to linear combination of all features that we originally have, and that sometimes is not amenable to interpretation. So I think both approaches are useful. Maybe these are more useful for interpretation purposes, but if maybe the case is that you're interested in prediction rather than recovering the correct support, then that may be the way to go.
Any other questions? Okay, then let's thank you.